basis, script B, is going to consist of the vectors 1, 2, and negative 1, 3. So that these vectors are your vectors v1 and v2 in the basis. So here's v1, here's v2. You know, v1 is the vector 1, 2. Relative to the basis b, that vector is represented by 1, 0. Because it's 1 times the v1 vector plus 0 times the v2 vector. Okay, so it's got representation 1, 0. 1, 0, b in the basis b means 1 times the v1 vector plus 0 times the v2 vector. Similarly, 0, 1, b means 0 times v1 plus 1 times v2. And of course, that's just equal to v2, negative 1, 3. So v2 is a vector negative 1, 3, but relative to the basis b, it's represented by 0, 1. Okay? Now we have a transformation in the matrix for the transformation relative to the basis b is 3, 0, 0, negative 2. So what does that do to the vector v1? What does it do to the vector v2? Well, v1 in the basis b is 1, 0. So if we multiply the vector as it's represented in basis b by the matrix relative to basis b, we get 3, 0, 0, negative 2 times 1, 0. Clearly, that equals 3, 0. And I don't think I wrote down 3, 0, okay, but it equals 3, 0, or 3 times 1, 0. And that's what we're saying here. Okay, and clearly this is true. My hesitation was I thought I'd probably written down column 3, 0, and then factored out the 3, but I just did it all at once. Okay. And I'm not even sure why I wrote it like that. It's not false, but right there's my 3, 0 that I was thinking about. Okay, so we have 3, 0. So again, we should understand easily that this matrix times this column gives us 3, 0. Now that's according to the basis b. What does this mean? It means 3 times our first basis vector plus 0 times our second basis vector. So that's 3 times our first basis vector, which is 1, 2, plus 0 times our second basis vector, which is negative 1, 3. And when we add those up, we get 3, 6. This, of course, is 0. Multiplying this through gives us 3, 6. And that's the vector in the standard representation. Okay, that's our actual vector in two-dimensional space, you can think. Okay, so T of V2 means, well, V2 is 0, 1 according to the basis B, so we multiply 0, 1 in basis B by our matrix relative to basis B, and we get our result 2, negative 6. So now we can draw a picture. Okay, we got our V1, we got our V2. 1, 2, 1, 2, and negative 1, 3. And the result of that is 3, 6. Okay, so we come over 3 up 6. And down here, 2, negative 6. Okay, that's what the transformation looks like. And what it does is it stretches everything along this direction because this vector is parallel to this one. And it stretches everything along this direction, but also flips it over in the opposite direction. And in fact, it stretches everything in this direction by a factor of 3. It stretches everything in this direction by a factor of 2, but also flips it, okay? Now, we want to figure out how to represent the vector 1, 0, according to standard basis, according to our v1 and v2 basis vectors for the basis B. So how do we do that? Well, we have to express 1, 0 as a linear combination of the two basis vectors. A linear combination of v1 and v2 is just c1 v1 plus c2 v2. And of course, v1 being 1, 2, v2 being negative 1, 3, we have c1 times 1, 2 plus c2 times negative 1, 3. c1 times our first basis vector plus c2 times our second basis vector. This translates immediately into a matrix equation, and we could verify that multiplying this matrix by the c1, c2 column gives us this. Excuse me, I'm just making sure I can breathe here. Not breathe, okay, making sure I can talk without coughing. So the 1, 0 vector is equal to this matrix times the c1, c2 vector. Okay? Now, what's this matrix? The first column is our first basis vector. The second column is our second basis vector. So I'm going to call this matrix the v1, v2 matrix. And I really don't need the comma there. So maybe I'll just kind of smudge that out, make a mess of it. Okay? Now v1 and v2, again, are the vectors from our basis B. So now we know that 1, 0 is this matrix, which is this matrix, multiplied by c1, c2. What we want to find is what c1 and c2 are. We're trying to find what multiple of v1 added to what multiple of v2 gives us 1, 0. Okay, well, if 1, 0 equals this matrix times c1, c2, then c1, c2 is this matrix expressed this way. Let's get rid of the comma. It's going to be the inverse of this matrix times 1, 0. Okay, so to find c1, c2, we invert this matrix multiplied by 1, 0. That's a very familiar step. Okay, we go ahead and proceed to find this inverse matrix. Okay, and I'm not going to go over the steps. We're going to find it, we're going to verify that it works, and then we're going to talk about where we are with this. So the inverse of your v1, v2 matrix, of course, is the inverse. Right there is your v1, there's your v2. We write down this matrix with the augmented matrix, reduce it, and we get this. So here's the inverse matrix. So this is the matrix inverse to this one. This is our v2, v1 inverse matrix. And to verify that that really works, let's multiply that inverse matrix by the vector 2, negative 6. Okay, now let's think about what this means before we go on. Okay, remember the vector 2, negative 6 is equivalent to this vector according to the basis B. Now, C1, C2 are the coefficients, are the numbers you need to multiply by V1 and V2 and then add the vectors in order to get 1, 0. So C1, C2 is the representation of this vector. The C1, C2 vector is a representation of the vector 1, 0 in basis B. Okay, well, if we multiply this inverse matrix by the vector 2, negative 6, which is equivalent to the matrix 0, negative 2, negative 2 times 0, 1 is 0, negative 2, relative to the basis B. If we do this multiplication, multiply this matrix by 2, negative 6, we in fact get 0, negative 2, which tells us that this matrix takes a vector in standard notation, standard matrix, relative to standard basis, and transforms it to a vector in terms of the basis B. So I could even put a subscript b on that vector to say that, that this matrix again transforms standard basis vector to the basis b vector. And I say C1, C2 relative to b for this solution would be the same as the vector 1, 0. And actually I should have said that before I digressed up here. Okay, in any case, this matrix takes us from the standard basis to basis b. Okay, this matrix would take us from basis b, the C1, C2 representation, back to the standard matrix, to the standard basis. And we're going to see how these are used to define what we call a similarity transformation. The key thing that you need to understand, the key matrix here, is this matrix of column vectors, the columns of the basis b. If we understand how this matrix works to transform a vector according to basis b to standard basis, then we understand that the inverse matrix transforms a vector according to standard basis into basis b.